Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome, everyone. I'm Dr. Mohamed Ali, and I'll be your lecturer for biostatistics this semester. You can reach me via email or mobile, and I'm happy to join any WhatsApp groups you might have.
Wa alaikum assalam, Dr. Mohamed. It's great to have you. I'm really looking forward to learning biostatistics. What exactly is it that we'll be focusing on?
Excellent question, Sarah. Biostatistics is essentially the application of statistical principles to biological systems. We'll be looking at how to collect, analyze, and interpret data from various biological experiments.
So it's statistics, but specifically for biology and medicine. That sounds fascinating.
Precisely. We'll cover everything from designing experiments to drawing meaningful conclusions from the results. Now, let's define statistics more broadly. It's a set of methods for collecting, analyzing, presenting, and interpreting data to make informed decisions. Biostatistics applies these methods to a wide range of biological topics.
That makes sense. So if we were studying the effectiveness of a new drug, we'd use biostatistics to analyze the trial data?
Exactly, Sarah. And medical biostatistics is a major branch, focusing on things like birth rates and mortality. It's all about making sense of biological data.
Okay, I'm starting to get a clearer picture. So the core idea is using data to make better decisions in biology.
You've got it. Now, let's dive into some fundamental terms. First, we have the population. Think of it as the entire group you're interested in studying. If we're studying the heights of students in this university, the population is all the students.
So if we're studying the prevalence of a certain disease in a village, the population would be everyone living in that village?
Precisely. And this population can be finite, like the number of students in a faculty, or infinite, like the possible weights of people, since weight can be measured with extreme precision.
Ah, I see. And when it's too large to study everyone, we take a sample, a smaller representative portion of the population.
Exactly. And what we study within that population or sample are called variables. These are the characteristics that can differ among individuals, like height or disease status. Now, variables can be broadly classified into two types, qualitative and quantitative. Qualitative variables describe categories or qualities.
Like gender, for example, male or female, or blood type, A, B, AB, O. Those can't really be expressed with numbers, can they?
You're absolutely right, Sarah. Gender, religion, marital status, blood type, these are all qualitative variables because they represent categories.
And quantitative variables are the ones we can express with numbers, like age, height, or weight, which can be ordered.
Yes, quantitative variables are numerical and can be ordered or ranked. We'll explore these more, but for now, remember the distinction between descriptive categories and numerical values. Within qualitative variables, we have two subtypes, nominal and ordinal. Nominal variables are categories without any inherent order, like hair color or marital status.
Precisely. Those categories are equivalent in terms of rank. What about ranking students by academic achievement? Would that be nominal?
Perfect example, Sarah. The order doesn't matter. Now, ordinal variables are qualitative, but they do have a natural order or ranking.
Like letter grades. A is better than B, which is better than C. Or perhaps the severity of a disease, like mild, moderate, severe.
Exactly. Letter grades, severity levels, these are ordinal. The ranking matters, but the difference between ranks isn't necessarily consistent or measurable in a numerical sense. Speaking of ordinal variables, Likert scales are a common way to measure them. Here we see examples like level of agreement or level of importance, where responses are ranked from, say, strongly disagree to strongly agree.
Precisely. It's about the order rather than the exact distance between categories, which is a key distinction in statistics.
Precisely. The scale provides an order, but the intervals between points aren't necessarily equal. It's a qualitative measurement with an ordinal structure.
It's helpful to see these concrete examples. It really clarifies the concept of ordinal data.
Indeed. Now, let's shift our focus to quantitative variables. Quantitative variables, which are numerical, can be further divided into discrete and continuous. Discrete variables are those we can count.
So, like the number of students in a classroom, or the number of cars produced in a factory. You can't have half a student or half a car.
Absolutely. They take on specific countable values. Now, continuous variables, on the other hand, can take on any value within a given range.
Like height or weight. If one person is 1.75 meters tall, another could be 1.755 meters, or 1.7552 meters, and so on. There are infinite possibilities between two values.
Exactly. Time, speed. These are typically continuous because they can be measured to a very high degree of precision, allowing for an infinite number of values within an interval. To recap, we can visualize the classification of variables like this. Data can be qualitative or quantitative. Qualitative variables are either nominal or ordinal. Quantitative variables are either discrete or continuous.
So, if I have data on people's eye color, that's qualitative, and since there's no order, it's nominal. If I have data on the number of children in families, that's quantitative and discrete.
Perfectly stated, Sarah. You're grasping the hierarchy. This tree diagram is a great way to remember how everything fits together.
It's like a flowchart for understanding data types. That makes it much easier to classify new information.
Indeed. Now, let's talk about how we handle raw data. When we first collect data, it's often in its raw, unorganized form. For example, a list of student heights as they were measured, 66, 64, 68, and so on. This is called raw data.
And if we want to make sense of it, we need to organize it, like arranging it from shortest to tallest.
Exactly. When we arrange raw data in ascending or descending order, we call it array data. This makes it much easier to see patterns, like the shortest and tallest individuals.
So, column 1 would be the raw, messy list, and column 2 would be the neat, ordered list. Got it.
Precisely. And this organization is the first step towards more complex analysis. One of the most fundamental ways to organize data is through a frequency distribution. This is essentially a table that organizes raw data by grouping it into classes and showing how many data points fall into each class.
So, if I have data on how many students scored a certain grade, the grade would be the class and the number of students would be the frequency.
That's a great way to think about it. The class represents a range or category, and the frequency tells us how often that class appears in our data.
It sounds like a way to summarize a lot of raw data into a more digestible format.
Exactly. It makes it much easier to see the distribution of the data. Let's look at an example. Imagine we roll a die 30 times and record the results. Here are the raw numbers. To create a frequency distribution, we list each possible outcome, 1 through 6, as a class, and count how many times each number appeared.
So, for the number 1, it appeared 5 times. For 2, also 5 times. And 3 appeared 8 times. The total frequency adds up to 30, which is the total number of rolls.
Correct. We can also calculate the percentage for each frequency. For example, 5 out of 30 rolls is about 16.67%. This gives us a clear picture of how often each outcome occurred.
This makes it so much easier to see that 3 was the most frequent outcome in this particular set of rolls.
Indeed, this is a basic frequency distribution. Now, what if our data isn't just discrete outcomes, but ranges of numbers? Here, we have data on record high temperatures for 50 states. Since temperature can vary continuously, we'll create a grouped frequency distribution using 7 classes.
So we find the highest and lowest temperatures, calculate the range, and then divide that range by the number of classes, 7, to find the width of each interval, which is about 4.9. We round that up to 5.
Precisely. And we start our first class at the lowest value, 100. With a width of 5, our classes would be 100 to 104, 105 to 109, and so on. Then we count how many temperatures fall into each class.
I see the table shows frequencies like 2, 8, 18, and the total frequency is 50, matching the number of states. We can also see the relative frequency and percentage for each class.
Excellent observation. This grouped frequency distribution helps us visualize the spread of temperatures across different ranges.
Now, when we work with these classes, especially for calculations later on, we often need a single representative value for each class. This is called the class mark, or midpoint.
How do we find that? For the 100-104 class, is it just the average of 100 and 104?
You've got it. We add the lower and upper limits of the class and divide by 2. So, 100 plus 104 divided by 2 equals 102. This 102 represents the midpoint of that temperature range.
So, for the 105-109 class, the midpoint would be 105 plus 109 divided by 2 equals 107. This is useful for graphing or further statistical analysis.
Indeed. It gives us a single value to represent the entire class interval. Finally, let's touch upon the sample proportion. This is a way to express the proportion of observations within a category in a sample.
Precisely. That's an accurate representation of the sample proportion for women in that specific sample.
Exactly. The formula is number of observations in category divided by the sample size. So, 300 divided by 500 gives us 0.60, or 60.
And if a machine produces 100 parts and 5 are defective, the sample proportion of defective parts is 5 out of 100, which is 0.05, or 5%. That seems straightforward.
It is. It's a simple yet powerful way to understand the prevalence of a characteristic within a sample. And that brings us to the end of Chapter 1. We've covered the essence of statistics, biostatistics, and the fundamental concepts of data types and organization.
Thank you, Dr. Mohamed. This was a very clear and engaging introduction. I feel much more comfortable with these foundational ideas now.
I'm delighted to hear that, Sarah. Remember to review the material, and I look forward to seeing you all in our next lecture. Peace be upon you, and God's mercy and blessings.
Wa alaikum assalam wa rahmatullahi wa barakatuh.